So the last practicum is meant to give you a bit more information about the analysis and study of stochastic models in R. I'm going to be going over the following topics. First of all, I'm going to spend some time describing discrete time Markov chains, giving you a bit more mathematical content there. Just a little time more on continuous time Markov chains, and a few words about stochastic models in R, and in particular I'm going to be discussing parallelization of the code. So let me move here. The first part of this lecture, well, this practicum, is about discrete time Markov chains, and we're going to go through the topics that are highlighted there. How do you formulate a discrete time Markov chain, really from a, like, what is it mathematically? And then what can we say about the asymptotic behavior of a discrete time Markov chain? And we will see that this particular aspect involves two different types of chains. So we have two different types of answers depending on whether we have a regular discrete time Markov chain or an absorbing discrete time Markov chain. And I will give a couple of examples with more numerics. So first of all, when I say formulating, it's really what is a discrete time Markov chain? Where does it come from? And this is like, it complements what we've seen before. So by the way, it's allergy season. I hope I won't break down throughout the presentation. But so I remind you that the overall idea of a discrete time Markov chain is that you have a bunch of states that we've denoted SI, and we're looking for some way to describe the evolution of a system with those states. And we denote Pi of n, the probability that a given state I will occur on the nth repetition of whatever experiment we're carrying out, where R is the total number of states. Now, we don't allow for the system not to do anything. So we're assuming that whatever happens, something must happen. And that means the system must be in one of the states we consider. That means that if I'm looking at the nth repetition of my experiment, then at that nth step, one of the states must have happened, at least one. Okay, so because I'm looking at probability to be in a state, so that means that the probability to be in one of the states must sum to 1. I must be in one of the states. Okay, and so if I look at the probability that sorry, I need to move myself out. So if I'm looking at the probability that I'm in state Si at time n plus 1, so n is the time essentially, then there's several ways for me to be there. So I could have been, for instance, at the previous step, I could have been in state 1. And the probability of being in state 1 in the nth step is P1 of n. Okay, we've just defined this. And we define P at 1i to be the probability to be in state 1. To go from state 1 to state I. Okay, so the probability that I'm in state I, given that I was in state 1 the previous time unit, is P1i, so the probability of going from 1 to I, given that at time n I was in state 1. And then I can continue the same way. I could have been in state 2, which I was with probability P2 of n, and then I moved from from state 2 to state I, and so on and so forth, all the way to R. Okay, so the probability that I'm in state I at time n plus 1 is simply the sum of all these individual probabilities. Okay, so it's the probability that I'm in state I given I was in state 1, or, so a plus from a probability side, or I was in state 2 and I moved to state I, or I was in state R, the last state, and I moved in state I. And so I get this probability of being in state I at time n plus 1 is simply this sum here. Okay. Now, that is true for all states I from 1 to n. So the probability that at time n plus 1 I'm in state 1 is given by this sum of products. That I'm in state k is given by this sum of products, all the way to state R, where I am with this probability here. And what you can see right away here is that this looks like a linear system. Okay, so if I look at it in matrix form, I can write this as, if I think in terms of a row vector, okay, I can write this as the probability at time n plus 1, where probability is this row probability vector, okay, is the probability at times n times some matrix P, and that matrix P is what we call the transition matrix. Okay, it's an R by R matrix, and it has entries, the probability ij of moving from state I to state j. Okay. So what we have is this system here. And okay, so this gives the same thing here. Now, the matrix P that we saw here, it has a specific form. So if you remember, every time here I have a probability, and I have to have that this sum has to be equal to 1 every time. Okay, so we say that a matrix is stochastic if the rows, so this is the sum of the entries on row I. Okay, so this is the row sums. So if all row sums are equal to 1 for all I, so if all row sums are equal to 1. And I should point out, typically we would say that the matrix here is row stochastic. It could also be column stochastic, where the columns would have sum 1, or it could be doubly stochastic if it had both row and columns equal to 1. When you have a stochastic matrix, it's a non-negative matrix, okay, but it also has row sums equal to 1. If you have a stochastic matrix, then there's a property that says that all eigenvalues of A are with modulus less than 1. So the spectral radius of the matrix is 1, because, I should add, because lambda equals 1 is an eigenvalue. And this is very easy to see. If you write the fact that the row sums are 1 in vector form, matrix vector form, what you are doing is you're multiplying the entries in M by a column vector of 1s, okay? And when you write that, when you say that the right-hand side of these sums is equal to 1, that means that M times that vector of 1s is equal to the vector of 1s, which tells us that 1, the number 1, is an eigenvalue associated to the eigenvector 1, with all 1s now. Okay. Now, that's very briefly how we define a discrete time Markov chain. So now, what's the long time behavior of these chains? So the easy thing to do first is to consider what happens when you iterate, because a Markov chain, the way it's written, you can see this is a discrete time equation. It's a sequence. I start with an initial value, I apply the projection matrix, the transition matrix every time, So this is what happens. If I start with an initial row probability vector that tells me what the probability of the state being in all the components is, then the first iteration, P of n, where P of n plus 1, where n is 0, is given by my recurrence formula here. Okay, P of n plus 1 is equal to P of n times P, capital P. So P of 1 is P of 0 times P. P of 2 is P of 1 times P, but P of 1 is P of 0 times P. So that means this is P of 0 times P squared. And what is going to happen is that this continues and we can iterate. And it's easy to see that in that case, if I want to know the state at time n of the Markov chain, the distribution of probability at time n of the Markov chain is simply given by P of 0 times the transition matrix to the nth power. Okay. Therefore, if I want to know what the long-term behavior of the system is, the Markov chain is, I need to compute this limit. And that limit is given by this. And P of 0 is a constant, okay? So I can pull it out of a limit. So I get that this is P of 0 times the limit when n goes to infinity of P of n, P to the n. But I'm not saying yet that this limit exists, okay? The limit of P of n is equal to this if this limit exists. So does it exist? Well, there's a nice property of stochastic matrices is that if you have two stochastic matrices and you multiply them together, and of course, they're compatible sizes, then you get a stochastic matrix. So that means in particular that any power of a stochastic matrix is a stochastic matrix. So this P of P to the n here is a stochastic matrix. But what happens in the long term now depends on what type of chain we have. And there's two main types of chains. There are regular Markov chains, as we're going to look at right now, and there are absorbing Markov chains. So regular Markov chains, I will point out, they are not very, very much used in disease models, because in most disease propagation models, when you have something like a state I equals 0, it's going to be what we call absorbing, and I'll come back to that later. When you have an absorbing state, you don't have a regular Markov chain. You have an absorbing Markov chain, and therefore what I'm going to be talking about right now is not applicable. But it's still worth taking a look at because it illustrates many aspects in many interesting aspects in population dynamics. And also, for instance, although it won't play a role when you're modeling disease propagation itself, a regular discrete time Markov chain might come into play if you're looking at how people move between locations, for instance. That would not be absorbing, typically. And so in that case, you might have a regular Markov chain. So understanding what happens to those chains is not something that is superfluous. So what's a regular Markov chain? So a regular Markov chain is a chain, and I should point out, these are, I'm giving definitions and so on, but this is not the way I would do it in a proper Markov chain course. We would go through much more detail. This is a high level approach to the problems. So a regular Markov chain is one where the transition matrix P is such that for some value k, some integer k positive, P to the k is a positive matrix. Okay, it has only positive entries, no zero entries. And I'll point out that this is equivalent to saying that the matrix M, or P, okay, is primitive, okay? The definition of a primitive matrix, forget that we're doing Markov chains here. Think about a non-negative matrix M. It is primitive if and only if there's an integer k such that M to the k is positive. So you can see that the two are equivalent. And in practice, what we're going to say often is that the Markov chain is regular if and only if the transition matrix is primitive. So, and this is one of the very interesting aspects with discrete time Markov chains in particular, is that you can go back and forth between some properties that are more on the graph side, and I will explain where this is coming from, and some properties that are more on the matrix side of things. Okay, so in any event, we have a regular Markov chain if and only if its transition matrix is primitive. If we have a regular Markov chain, then the powers of the transition matrix approach a stochastic matrix. I should move myself here. So if the powers approach a stochastic matrix, each row in that stochastic matrix is a row vector, W1 to WR, that has positive components. Okay, so if we have a regular Markov chain, the limit of the Markov chain of the vector of distribution of probabilities is equal to P of 0 times the limit of Pn, and we just saw that Pn approaches the stochastic matrix, so this is P of 0 times W. Okay. And when we are trying to study this, I mean to use it, we'll end up using left and right eigenvectors. And so we've seen that already, but let me just sort of come back to this. If we have a matrix, then something that satisfies mu equals lambda u for u non-zero, I should point out this, is a right eigenvector, although we often omit the name right because that's the one we use most of the time. And if we have V transpose M, so row vector times the matrix equals lambda times row vector, then we have a left eigenvector. Okay? And each eigenvalue is associated to both a left and a right eigenvector. Well, of course, I should say a left and a right, of course, two multiples, because any multiple of an eigenvector is also an eigenvector. Now, the vector W that I'm looking for, it's the left eigenvector corresponding to the eigenvalue 1 of the transition matrix. Now remember, I was discussing earlier the fact that we know that the right eigenvector corresponding to the eigenvalue 1 is the vector of 1s, okay? Because P in here, P is such that P times the vector of 1s, the column vector of 1s, is equal to the column vector of 1s, because the row sums are all equal to 1. Okay, so W that we're looking for is actually the other eigenvector, so the left eigenvector this time, corresponding to the eigenvalue 1. And this is simple to see. So suppose that the system converges. Then what is going to happen is that Pn plus 1 is equal to Pn of P. And that is, like, this is the iteration formula, okay? But if I have converged, then I know that P of n is equal to P of n plus 1, okay? In the limit, they're all equal, okay? That means that my limit satisfies Wp equals W. And if you read this as an eigenvalue eigenvector equation, this is this is a row vector, okay? So this is the left eigenvector eigenvalue eigenvector equation for the eigenvector W associated to the eigenvalue 1. And I'll point out that sometimes if you're looking for left eigenvectors, you might be using a numerical solver that only knows how to do right eigenvectors, in which case it's very easy to do. If you can only compute the right eigenvector, you simply compute the eigenvector corresponding to the transpose of the matrix, okay? Because if I transpose this whole equation, I get what I want. Now, there's one little extra step that you might have to do to compute your eigenvector, is that when you've computed your eigenvector, what you get is a direction, and it might not be a vector of length 1. And here we want a probability vector. Okay, so it has to have length 1. So what you do is once you found your W, you divide W by the norm of W, which you take to be just the sum. Okay, and that gives you the normalized of a probability of a probability vector. Now, one remark that this I remarked on already, but let me say it again. In discrete time Markov chains in particular, but I mean, this is not the only place where you will see that. There's a nice relationship between some linear algebraic properties and some graph theory properties. So we say that a digraph, a directed graph, is strongly connected if you take any pair of vertices and you can find a path between these pairs of vertices. Okay, and we say that a matrix is irreducible if I can't find a matrix such that the matrix can be written as a block triangular matrix. Okay, block triangular, upper or lower, it doesn't matter. Okay, but so if I can reorder my rows and columns in a matrix in such a way that the matrix is block upper or block lower triangular, it is reducible. If I cannot do this, it's irreducible. This is sometimes difficult to check, but there is this very nice equivalency that if you have a matrix that's irreducible, this is equivalent to saying that the graph associated, the digraph associated to that matrix, okay, so that's the digraph where there is an arc from I to J if there is a non-zero entry in the matrix and no arc otherwise. Well, if the digraph is strongly connected, this is equivalent to irreducibility. So, for instance, this is a random walk. We'll come back to this. This random walk here has a strongly connected digraph, okay, because I can take any vertex and any other vertex, and I can follow a path to go from that vertex 1 to vertex whatever. Whereas this one here at the bottom is not strongly connected, because as soon as I make it here or at this endpoint here, I'm stuck. I cannot leave this state of this vertex. Okay, so this is strongly connected. This is not strongly connected. And in terms of detecting regularity, there's a theorem that tells us this is a sufficient condition for primitivity. It's that I have a matrix that's primitive if the associated connection graph is strongly connected and there is at least one positive entry on the diagonal. And I should point out that none of those graphs here satisfy this because I don't have a loop. Okay, a positive entry on the diagonal would mean that one of those vertices here has a loop. I don't have a loop here, which, I mean, as I said, this is that theorem is a necessary condition, a sufficient condition, sorry. And so there are other ways to guarantee primitivity, and that graph is actually that the matrix associated to this is actually primitive. Okay, so that graph is regular, that Markov chain is regular. But that's it. Okay, so but anyway, as I said, I'm not going to spend much more time on this regular case because it is not the most relevant in the epi context. But I will still show you very briefly to set up random walks, because we'll be using another random walk later, and two other random walks, I should say. So let me show you how you would analyze this graph that I showed you just before. Okay, so I have this Markov chain where I have P states, and this is, so another name for the random walk would be a drunk man's walk. Okay, if you have a half here as the probability. So the idea is I have p states. That's why, like, it's called a drunk man's walk. It's the idea, the state could be where you are. And what happens is you have a probability 1/2 of going left and a half going right. So you don't know what you're doing. You either walk left or you walk right. And this is a random walk, okay? But as I said, you'll find it very often called the drunk man's walk also, or something to that effect. So you can see what's happening here. I am following. So for example, if I'm here, I will go left with probability 1/2 or right with probability 1/2. When I'm at the end points, I have a probability 1 of returning. Okay. So the transition matrix for this this random walk has super and supra diagonals equal to 1/2, and the first row and last row with just the probability of moving right in the first row and left in the last row. Okay. This is a primitive matrix. I'm not going to detail, but you can easily show that it's primitive. So if I want to study the steady state, I need to solve. So here I'm writing W as a column vector, but I'm making it a row vector. Okay, I need to solve WP equals W, which amounts to writing this system of equations. If I express everything in terms of W1, things sort of boil down to this. So what you get is the vector that is something like this: W1, two W1s, etc., two W1s, W1. And of course, remember that this is my left eigenvector corresponding to the eigenvalue 1, but I want my norm, I want the sum of my entries to be 1, and therefore I need to divide by, so when I take the sum of all entries, I get this, and therefore I need to take W1 equals to 1 over 2p minus 1. So this is the stationary distribution of probabilities. And you can see that what happens is that I get a half of the probability of being in the central states, in the extreme states, and then I get a probability, an equal probability of being in each of the states there. And I should point out the reason why it's this nice distribution like this is because I've made the probability 1/2 of going right and the probability 1/2 of going left. If I had a more varied, as I said, sorry, allergies. So if I had a more varied way of moving left and right, depending on where I am, for instance, the vector would not look like this, of course. And if I wanted to say, for instance, what happens if I start with probability 1 in state 1, so that means I am always in state 1 at the beginning, okay, then I would compute the limit by just taking that p of 0 times wt, and so I would get something like this. Okay. Now, let me show you the numerical side of this. So I'm going to set up, just so that we can read, I'm going to just take 10 states, but you could do whatever. I'm going to define a probability of moving left, probability of moving right, and actually we could make it to have loops. I'm not using loops here, but I'm just saying the probability of staying is just going to be 1 minus the sum of the probabilities. And for the transition matrix, it's quite simple. If I'm in the middle, everything except the first and last row, I just say the probability of going left is the probability of going left, probability of going right is probability of going right, and on the diagonal, I have a probability to stay, which if I put half and half here is 0. And then in the first row, I can only move right. I can go from 1 to 2. This is probability 1. And on the last row, I can only go from number of states to number of states minus 1, so left, and I'm putting 1 here. And I'm going to use the Markov chain library, which I briefly mentioned in the Stochastic systems lecture. Just use the library, define the Markov chain. So this is saying implement a new Markov chain where the states I'm going to, this is just the names that I'm going to give to them. So this is saying that so sprintf is a very useful function. It just prints this, where %d is replaced by %d stands for placeholder for an integer. And the integers I'm going to replace %d by are the numbers from 1 to number of states. Okay, 1 to blah, 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 10 here. So that the name of the states are going to be S1, S2, S3, etc. up to S10. The transition matrix I specify as this matrix T that I just made. And I'm just going to give it the name random walk regular. There's a bunch of functions that I mentioned in the first stochastic systems lecture, but let me briefly go over what you could do. So the first one is a summary. So the summary is going to give you some summary information about the chain. So this is the name of my chain. It's a Markov chain that is composed of closed classes and one recurrent class. So because this is like a set, okay, so the set of recurrent classes is in this case 1, and all of the classes are recurrent. There's no transient classes. We'll come back to this. The Markov chain is irreducible, which is another name for regular, and there's no absorbing states. Of the functions we had before, there's a bunch that are not useful because we're actually in a regular case. So all of those functions will return things that are either don't mean anything or are trivial. So these will not be useful here. But for instance, let me compute the steady states. And this is that vector WT that I computed. And you can see that we get, so remember the number of states here is 10. And I get 1 over 2 divided by 9 here. This is 1 over 9 and etc. So this is exactly what we had computed analytically. Other properties that I can get, I can compute the mean recurrence time. So this, if you look at the definition of a function, it outputs a vector with the expected time to first return to a state when the chain starts there. Okay, and the states are present in the vector only if they're recurrent. And if you remember the summary we had, the recurrent states were those here. So that's why we have all states here. So this tells me that on average, okay, this is a mean, on average, if I start in S2, it will take on average 9 iterations before the system returns to state 2. Whereas if so this is the same for all the intermediate states, let's say, and the end states, of course, it's less likely to end up there. And so it's on average, if you start at the end, it will take 18 times until you come back. Another question you might ask is the periodicity of the Markov chain. So this is for a reducible Markov chain. So regular Markov chains. And so the period of a state is given by this, and the period of a chain, because that chain is irreducible, the period is the same. And this is simply, if you want to sort of think from a practical point of view, is what's the minimum number of jumps that I need to do before I can return to myself, if I start in S1, for example, how long until I can return to S1. Okay, and this chain, remember, has no loops. So every time if I want to return, if I'm in S5, for example, and I want to come back to S5, I have to go, for instance, S6, S5. And this is what this is saying. Okay, the period 2 is this. The mean first passage time is an interesting measure. So suppose you have an irreducible regular Markov chain, the expected number of steps to reach other states. So if you start in S1, of course you look at all the other steps, not just the diagonal. You see the diagonal is 0, it's for the other states, not the state and the others. So from S1, on average, it'll take me 1 step to go to S2. And yes, because there's a probability 1 of going from S1 to S2. So that one is very simple. But for instance, from S1 to get to S3 is not as clear, because I could go S1, S2, S3, but I could also go S1, S2, S1, S2, S3. Okay, so that's why that number is not 2, because I can still move left once I've moved to S2, and so on and so forth. So this is going to give you the average number of steps before you go from a given state into another one. Okay. So this is interesting. For example, on average, it will take you 81 steps to go from one end of a chain where we have 10 states. One end of a chain to the other end of a chain will take 10 steps. 81 steps, sorry. Now let's move on to absorbing chains, which are much more useful in the disease modeling context. So a chain is absorbing if it has an absorbing state. So let's start with the definition for an absorbing state. So a state SI is absorbing if whenever you hit that state at a given time, you remain in that state for every subsequent times. Okay, so a state SI is absorbing in terms of the transition matrix if the probability of moving from I to I is 1, and the probability of moving from I to any other state is 0. Okay, so we, like in the transition matrix, that will mean on a given row, a state that is absorbing, its corresponding row in the transition matrix will have only a 1 on the diagonal. And a Markov chain is absorbing if it has at least one absorbing state. A state that is not absorbing is called transient. And I should say this is a very simple version. I have included 2 types of absorbing chains. And one of the types I included is a slightly more evolved, because you can also have absorbing subgraphs, okay? But for here, we're only going to focus on absorbing states. Now, if you have an absorbing chain, suppose something like this, caricaturing here, but I have 2 transient states and 2 absorbing states. There's a bunch of questions that we can ask. The first one is, what happens if I have a process that follows an absorbing, where the Markov chain is absorbing, do I eventually reach an absorbing state? Then other questions might be, how many times on average am I in a transient state if I start in a transient state? What's the average number of times before I am absorbed in one of those 2 states here? And what's the probability that I will be absorbed by, say, state 1 here, if there's more than one absorbing state, if I start here, or if I start here? Okay, and these are all questions that we answer using linear algebra. except for this first, well, I mean, this is more a probability issue. So the first question, which was, what's the probability of reaching an absorbing state? Well, in an absorbing Markov chain, with probability 1, you'll end up in an absorbing state. It might take the chain very, very long until it does end up in an absorbing state. But from a probability point of view, the probability is 1 that you will be absorbed. Okay. Now, if you have an absorbing Markov chain, the equivalent, from a matrix aspect, this means the transition matrix is reducible. I was talking before about irreducibility. Well, in the case of an absorbing Markov chain, we have a reducible Markov transition matrix, which means that, remember what I said, a matrix is irreducible if it cannot be written in block triangular form, or a matrix is reducible if I can write it in block triangular form. And here, what we are going to call the standard form of the transition matrix, or the canonical form, there's a variety of names, is the following. So if I have an absorbing Markov chain, then I am going to be able to write the transition matrix the following way. I'm going to have a matrix K, identity K here, with K equal to the number of absorbing states. Okay, so if there is one absorbing state, I'll have a 1. If there's 2 absorbing states, I'll have a 2 by 2 matrix, the 2 by 2 identity matrix, and so on and so forth. Then I'll have a matrix here, R, that will describe movement from transient states into absorbing states, and a matrix Q that is going to describe movements, so transitions within the transient states. Okay, so this matrix and this matrix are square. This matrix and this matrix need not be square. Okay. They're only square if these two matrices I and Q are of the same size. Okay, otherwise they're like rectangles. Now, I'm not going to show it. It is not too complicated to show that when you look at the matrix, so the Q here, if you subtract it from an identity matrix of the appropriate size, you have an invertible matrix. Okay. And given that you can do that, we then define n to be the inverse of this matrix. And that is what is typically called the fundamental matrix of the Markov chain. And then we can take the row sums of n, okay? This is going to be a vector. And we can also create the product n times R. So remember that R is this matrix here that describes transient states to absorbing states. So if I create these three matrices, then the questions that I was asking before in terms of time to absorption are answered by those matrices. So that matrix, the fundamental matrix, the inverse of identity minus Q, contains the average number of times the process is in the jth transient state if it starts in the ith transient state. Ti contains the average number of steps before the process enters an absorbing state if it starts in a transient state. This is not telling you which absorbing state it enters, just how long it remains in transient states before it is absorbed. And B gives you the probability of entering the jth absorbing state if you start in the ith transient state. Okay, and I'll point out there's an old book by Kearney and Snell that has some very good things about the linear algebraic side of these problems. So let's look at another random walk. So this is the second case I was showing earlier. It's the same setup as we had before, except that I'm assuming that the endpoints S1 and SP are absorbing. So the setup is going to be the same as before, except that this first row and last row, if you remember, the first version of the random walk had a 1 here and a 1 here. Here, this is an absorbing Markov chain, so the 1 is on the main diagonal. Put it in standard form, well, that's easy. What you do is you first list the absorbing states and then write the other states. So S1 and SP, both endpoints, and then all the others. And once you have the S1 and SP and so on, you can actually work through the details of what those probabilities are. Okay, so, and you can see this is the identity 2 that I was talking about before. And then this block that starts here and goes to the bottom is the matrix that we denoted R. This one is a block of zeros. So if you have anything else than zeros in here, you know you have a problem. And this rectangular block here is the matrix that we denoted Q. So this is what I'm writing here. Okay, so I get an identity 2, I get my matrix R and my matrix Q. That's it. So I minus Q inverse, and I'm going to point out that I have detailed in the notes. I have detailed in the following few slides how you could invert this matrix. I'll point out that it's not required numerically. You can invert it much more easily. This is just to show you that you can here in this instance compute explicitly the inverse of this matrix I minus Q. It's not easy, and it takes a few steps. Oops, I should move. It takes a few steps, but there are results on how to invert a symmetric tridiagonal matrix or a symmetric diagonal non-symmetric tridiagonal matrix. Things are sometimes complicated. This one is symmetric, so that's easy. And there's an algorithm that you can go through. You write a variety of expressions, and as I said, we're not going to spend a lot of time on this. I just want to point out that, okay, you get to some point where J inverse is the matrix that I want, and I can compute explicitly those terms. Okay, but because it's easy to do numerically, let's not worry about this. I mean, I just wanted to point it out because, yes, there is actually a way to do it explicitly. But let's do as we did before. So a small number of states. This way we can see what's happening. The same way as before. Actually, the only thing that changes compared to before is this one. Now, instead of writing that I'm moving right when I'm at 1 and left when I'm at number of states, I'm staying there. So when I do this and then I use this as my Markov chain in the library Markov chain, I should remove this. These are the functions I can use. So the functions that I can use now are not the same. Okay, there's a bunch of functions here that won't make any sense. But okay, let's look at the summary. So this is the absorbing random walk. It has closed classes 1 and 10. It has recurrent classes. And you can see that before we had recurrent classes was the entire set of classes because we were going back and forth. Here, these are the recurrent classes, 1 and 10, so the absorbing states. The transient classes is this group of classes. The Markov chain is not irreducible. In other words, it's absorbing. And I should point out, I'm making the sort of shortcut here to say that it's not irreducible is equivalent to absorbing, but there will be intermediate cases, okay? More interesting cases, I should point out. But, okay, and it's detected that the two absorbing states are 1 and 10. No, so these are not useful in this case because we're absorbing. So one thing we can do is we can ask for the canonical form. And I should point out, we could have asked for the canonical form in the regular random walk case, but what we would have got is exactly the transition matrix. But here, look, it's done exactly what we were discussing. Sorry, so I'm looking at this. It's put the states as S1, S10, and then the transient states. And it's showing you what it's done with the transition matrix. So I have identity here. I have below my matrix R. And here I have the matrix Q. Okay, so it's done the partition. And here we can compute, for instance, the mean absorption time. So this time, we're only looking at the mean absorption time when you are in a recurrent state, okay? Not in a, not recurrent, in a transient state, okay? Not when you're at one of the absorbing points, because at that endpoint, you're absorbed right away. So what this is saying is that it takes, on average, 8 steps to be absorbed. So that's the TI, okay? I should have pointed out what the matrices were. This is the row vector or column vector TI that we derived. So this says, on average, it will take me 8 steps before I'm absorbed if I started in state 2. If I started in state 3, on average, it will take 14 steps before I'm absorbed. But it's not saying where you are absorbed. This is, what did we call it? B equals NR. So this is the probability that I will be absorbed in S1 or S10 if I start in one of those transient states. Okay, so for instance, and remember what the chain looks like, it's 1, 2, etc. And so if I start close to S1, then I'm much more likely to be absorbed in S1, which is next door, than in S10, which is at the other end of that chain I took. And you can see things sort of switch over when we get to when we switch from 5 to 6 as our initial condition. And when we switch to 6, then we become more likely to be absorbed at the other endpoint. And again, of course, this sort of regularity in the behavior comes from the fact that I'm assuming that you have a probability of 1/2 of going both ways. If the weights were not the same, then those probabilities would be different as well. Hitting probability is an interesting thing that you can use. So this is if you have a Markov chain. If you have a Markov chain, this function calculates the probability of ever arriving from state I to j. So what this is saying is if I'm starting in S1, what's the probability that I will end up in one of those states? And remember, S1 is absorbing. Therefore, the probability, if I start in S1, with probability 1, I will end up in S1, and with probability 0, I'll end up anywhere else. Okay, so this is giving me a little bit the same information as the previous one, but with also the probabilities for the absorbing states. Okay. And the last thing I want to do on these discrete time chains is to go through quickly the discrete time SIS system that we already saw. Remind you that the chain looks like so. So we assume that the total population is constant, and therefore we can just consider the i's, and we look at the probability of moving right, which is given by beta si times delta t, the probability of recovering, which is gamma times I delta t, and the probability of nothing happening, which is simply the complement of these two probabilities. And I'll remind you the remark that I made. I mean, so by playing with delta t, essentially you make sure that you have a probability matrix. So when you're looking at this problem, you end up with a transition matrix that looks something like so. So the first row corresponds to an absorbing state. Now you know what that means. So there's just a diagonal entry, and then the subsequent rows allow to move left by recovery, right by infection, or stay in place, and except for the last row, which allows just to stay in place or recover. So, and I showed this briefly also during the stochastic systems lecture, but let's go over it again. So as before, and I'll just make it even smaller so we can see things better. Take a total population of 5, which is completely unrealistic, but never mind. We make the transition matrix, and this is just checking that we are not making too large row sums. And if we make too large a row sum, the largest row sum we simply make equal to 1. And then we make the diagonal by taking 1 minus the row sums. So again, we use the Markov chain library using the transition matrix T. We say that the states go from 0 to population. So remember that we have to start with 1 more than the total population because we're looking at I, and I can go from 0 to the total population. So we have, if pop is 5, we need 6 states. Then the summary, which I had already shown, I think. This is a Markov chain that has I0 as closed classes, I0 as a recurrent class, and a transient class is other states. The Markov chain is not irreducible, and it has a single, in this time, a single absorbing state I0. The canonical form is simply has a 1. Well, I mean, the matrix was already in canonical form in this time, so we don't need to do anything. We just list the values as they were before. Steady states. So you could do steady states here, but steady states is always going to be weird. So yes, in the end, well, in an absorbing chain, I mean, because what does that mean? Well, there's one absorbing state. Therefore, eventually, because the probability of ending up in the absorbing state is 1, well, that's where all the mass is. The hitting probabilities, well, you can see that because I equals 0 is an absorbing state, wherever I start from, with probability 1, I'm ending up in I equals 0. Okay, and you can see how things work. So this means, what is the probability that I will hit I equals 1 if I start with I equals 5? Well, as I'm being absorbed, as I'm making my way left in the random walk towards I equals 0, I am going to cross all other states. Okay, so the probability that I'll go through I4 is 1. Probability that I'll go through I3 is 1, and so on and so forth. So this is what this matrix is saying. Okay. The mean absorbing time, these are interesting. So if you start with 3 infectives, for instance, with the parameters that I've used and so on, because here progression to the right is different from progression to the left. And so the situation is very different from those homogeneous random walks that I was looking at before. And you can see here, for instance, that I've taken an R0 that's big enough that if I start with I equals 1, then typically it will take some time because before I'm absorbed, because I'm going to first try to go right. Okay, well, this is what this is saying here. It will take on average 24 steps before I'm absorbed, which means that I'm much more likely to go right than to go left. Absorption probabilities, well, of course, there's a single absorption absorbing state, I0, and with probability 1, all the transient states are going to end up there. Okay, so this is it for discrete time Markov chain. There is a lot more to say, but I'm not going to do anything else here. As with other topics in this course, if you there are other references that I recommend if you want to read more about this. Now let's look at continuous time Markov chains very quickly. As I said, the first thing I want to, well, no, first thing, the only thing I want to do about Markov chain is just to show you. So I've defined Markov chains in a certain way, and I just want to point out that you can define continuous time Markov chains in a variety of ways. Okay, so one, probably the best way to define a Markov chain is as such. So you take some delta t and you look at the probability that at time t plus, oh, this is a delta t here, at time t plus delta t, I will be in state j. If I'm in state I as, this is for I of t, okay, this is an SIS model that I'm thinking of here, or birth, sorry, this is birth and death. So at time t, I was in state I, and at time t plus delta t, I'm in state j, and these have probabilities that depend on delta t, that is given by, this is the birth term, so this is saying j is I plus 1, so I've increased I by 1, capital I by 1, okay. So this has probability bi delta t plus a little o of delta t. Death takes me left, okay. This is going from I equals some quantity to I equals that quantity minus 1. The complement is this, and the probability of something else happening is a little o of delta t, and that little o of delta t goes to 0 as delta t goes to 0. And so I should point out, so what happens is that you let delta t go to 0. Now, what we call a forward Komogorov equation is defined the following way, and there would be a lot more to say about this, but I'll just briefly define this. So you see these quantities we defined here, we can use them here, and this is going to give us the probability that I'm in a certain state at time t plus delta t as a function of the probability that I'm in the other, well, all the possible other states at time t. Okay, and then what you can do is take the limit, so this is the derivative, okay, and take the limit when delta t goes to 0, and then you end up with these equations that are called the forward Kolmogorov equations. And I haven't put any proper use of this in the examples. This is just to bring up this topic. I should probably have more details here, but for now, this is all I'll do. Perhaps I will add more content in revision of these notes. So the previous system you can write in this following form. And what's nice is that you can then compute the evolution of the state as given by your forward Komogorov equation using the matrix exponential of the matrix Q. And what's also important is that there is a link between discrete, oops, oh yes, that's good, I can see things. There is a a link between discrete time Markov chain and continuous time Markov chain when you make delta t small. So if you remember, the discrete time Markov chain takes this form, and if you let delta t go to 0, then you can get the forward Komogorov equation for the continuous time Markov chain, and you get them through the transition matrix this way. Okay. As I said, this would warrant a good 30 or 45 minutes more. If I'm courageous, I will detail this more in a future lecture, but for now, I'll stop here. And the last thing I wanted to do was to make a very brief remark about stochastic models in R. I've sort of walked around this topic a few times. So, which is when it's in particular when you're doing things like continuous time Markov chains or discrete time Markov chains for that matter, or even if you're doing deterministic simulations, but you are considering such problems as, for instance, sensitivity analysis, which requires you to evaluate the behavior of the system for a wide range of parameter values, for instance, then it's a good idea to try to parallelize your code. So, and I sort of did the preparation step in the first lecture about using R, when I insisted on the fact that it's good to know how to use lapply. And so let me show you here how you would go from using lapply to parallelly to do the same type of problem as we've done before. So this function here just detects the number of cores, and if you don't have a lot of cores, I really recommend that you leave one alone. That sort of will forbid your computer from completely freezing if your code is well parallelized. And then you need to issue a few commands. So this one, for instance, is make a cluster. So this just creates a cluster that has a number of cores. And here, this is the simple cluster where all the cores that you're using are on the same computer. It is possible to do the same thing with multiple computers, but it is a little bit more complicated. So I'm going to stick to the idea that you want to use several cores on your computer, not several different computers. But I'll point out the idea would be essentially the same, except that it's a little bit more complicated. So this makes a cluster. These two commands are important because what happens when you make your cluster is that you have to, so there's those so-called workers that are sort of detached, parallelized. What they are essentially is an R script. Remember, you can run R from the command line. So it's essentially an R version that's running, and that is listening to commands from the main R code. So when these R sessions are created, they know essentially nothing. So these two instructions here, this one evaluates this command on the cluster. Okay, CL is the cluster, and what I'm doing here is I'm evaluating this command, library Gillespie SSA2. I'm getting each cluster worker to run this command. There could be a better way to do it. I actually don't need to evaluate the whole library. I just need to make each node, each worker, aware of the function I want to use. But this is one way to do it. Another way would be with cluster export. Okay, so cluster export here is I'm exporting my parameters. So I'm making each worker aware of the value of the parameters. And this is a function. and I'm making each cluster, each worker aware of those functions. Once this is done, all I need to do is, remember we had an L applied. Well, it's the same, except that I'm using par L applied for parallel L apply. I need to say what cluster I'm working on, which is that cluster I just made. I need to say what my function is applying to. Okay, and here I don't really need it. So essentially, I am not, you can see that function of x here does not involve x. So I don't care about this x, but you essentially, if I remember well, at least before, you used to have to name it, even if you were not doing anything with it. And this is the function that I'm going to run one simulation. It's going to depend on the parameters, okay, that I've exported, and then you run the cluster. And as I point out, if you go to the GitHub repo, you have simulate CTMC parallel, which has this code. So this is a graph that you've already seen, and this is the way I'm making each of these simulations, each of these trajectories, is by running them separately in the cluster, okay, to the workers. So I don't remember how many there are, but this is how you get them. And just to sort of highlight why there is a benefit. So suppose that I was running code for 100 sims, and tick and tock, of course, measures the time between tick and tock. This is a MATLAB command that was adapted to R. So I don't remember what code I was running for the sequential version. Oh yes, that was a very complicated version because it takes a long time to run, but never mind. Whatever what that was running, I was getting 66 seconds for the parallel version. And if I do the same thing in sequential, which simply means that I replace par L apply by L apply, okay, and remove the CL equals CL command. And yes, one stupidity, I'll say it like this because it really is silly. The argument for the data in par L apply is capital X and little fun, whereas the argument for L apply is capital X and capital fun. This is a little frustrating, but if you do this sequentially, you get 318 seconds instead of 66. And that was on a 6-core, 12-thread machine. If I run it on one of my faster, more beefy machines, so for instance, a Threadripper with 32 cores and 64 threads, then it takes 12 seconds instead of 258 seconds in sequential. So that is a factor of 21.5 times, which is a very substantial speed up. So imagine if you have to do that many times, running things. For instance, if you have code that takes a day to run, if you run it in parallel, it might take about an hour, which is a very substantial improvement over a day.